Now it is your turn to build and stress this chapter's operations. In C we have 3 labs. Try each one yourself before you open the solution. In the first lab, you build insert, search, and delete over a fixed bucket array of string keyed chains. There is no rehashing yet. That comes in lab 3. Your first function is htinsert. It takes the bucket array, a key string, and a value. The second is htsearch. It returns the node for a key, or null when the key is absent. The third is htdelete. It returns 1 when it removes the key, and 0 when the key was not there. The fourth is htfree. It frees every node in every chain when you are done. To test, insert red, green, and blue. Search for green, which should be found, and yellow, which should be absent. Then delete red and confirm that green is still there and red is gone. One tip: htinsert must scan the chain first. If the key already exists, update its value in place. Do not add a second node for the same key. Give the whole thing a try before you look at the solution. This is one clean way to write it. Compare it with your own version as we walk the key lines. This is htinsert. It takes the bucket array, a key, and a value. First it hashes the key into a bucket index called idx. Then it walks the chain at that bucket, one node at a time until P is null. If the current node's key equals the new key, it updates the value and returns. That is the no duplicates rule from the tip. If the key was not found, it allocates a fresh node with malloc. This line sets the new node's next pointer to the current head of the chain. And this line makes the new node the new head. So the insert splices at the front of the bucket, which is big O of 1. Search is the same walk, with a different ending. htisearch takes the bucket array and a key. It compares each node's key against the one you want. On a match, it returns that node. And if the chain runs out, it returns null. Look at the output. After deleting red, searching for red returns null. And green is still found. Everything behaves exactly as the test asked. In the second lab, you compare a poor hash against a better one on the same word list. The poor hash just sums the character codes. The better one is DJB2. You measure the difference in the worst chain. The first function is sumhash. It adds up the character codes of the string. The second is DJB2 hash. It multiplies and adds as it goes, which is this chapter's own hash. The third is longestchain. You pass it a hash function and a table size, and it returns the length of the longest chain that hash produces. One tip: include some anagrams like listen and silent, same letters in a different order. Some hash cannot tell them apart, and that order blindness is the bug. Use table sizes that are not powers of 2, like 7 and 13. Try it yourself, then check your worst chain numbers against the solution. Let us walk the solution and see why the sumhash struggles. This is sumhash. It takes the string and the table size m. Inside the loop it adds each character code into a running total. Look carefully at what this does not do. The order of the characters never changes the sum. That is exactly why anagrams collide. Then it returns the total mod m, which folds the sum into a bucket index. Now longestchain. It takes a pointer to a hash function and a table size. Taking the hash as a parameter is what lets us run the same measurement over both hashes. This line hashes every word and increases the count for its bucket. So counts holds how many words landed in each bucket. Then it scans the counts and keeps the largest one in worst. That is the length of the longest chain, which is our measure of how badly the hash clumps. Look at the anagrams. Under sumhash, all 4 of them land on bucket 4. 4, 4, 4, 4. That is a worst chain of 4. Under DJB2, they spread to 5, 3, 5, 5. Not perfect, but better. So at table size 7, the worst chain drops from 4 to 3. And the same at size 13. A real hash still cannot promise anagram-proof spreading. It just needs to mix enough that most keys go to different buckets. In the third lab, you take lab 1's fixed table and make it grow. After every insert, you check the load factor and double the bucket count when it goes past 0.75. To do this, you change the bucket array into a table struct. It holds a pointer to the buckets, the number of buckets, and the number of items. Then tableinsert works on that struct. It can rehash internally, which means it can replace the whole bucket array when the table gets too full. To test, start with only 2 buckets and insert 6 keys. Print the bucket count and alpha before each insert, and confirm a rehash message fires right when alpha would cross 0.75. One tip: rehash before you return from the insert that crossed the threshold, not on the next call, and replace every existing node into the new array. Do not free and rebuild the nodes themselves. This is the challenge lab, so take your time before you look at the solution. Let us walk the solution. The rehash is the only new piece. Everything else is the chaining you already wrote. This is table rehash. It takes the table and the new, larger bucket count. First, it allocates a fresh array of empty buckets with calloc, so every new bucket starts as null. It walks the old buckets one by one and follows each bucket's chain. For each node, it first saves the next pointer before the relink can destroy it. This line rehashes the node's key against the new bucket count, because the bucket index changes when the array size changes. Then it splices the same node into the front of its new bucket. The node is relinked, not rebuilt. After every node has moved, it frees only the old bucket array. The nodes stay alive, so there is no leak and no rebuild. Now tableinsert. After it adds the item, it increases the item count by 1. Then it checks the load factor. If items divided by buckets is greater than 0.75, it triggers a rehash. Note the check runs before returning on the very insert that crossed the threshold. And the rehash doubles the bucket count, passing in buckets times 2. Look at the run. The table starts tiny with 2 buckets, so a rehash to 4 buckets fires early. By the end, there are 6 items in 8 buckets, and alpha settles at 0.75, and that is hash tables start to finish. Nice work getting through the whole chapter.